Alright guys, in this video we are going to be looking at exercise 11 of the electromagnetism tutorial PDF, and it reads: a rod of mass 0.72 kg and radius of 6.00 centimeters rests on two parallel rays as shown in the figure. That's the figure that's been displayed. The two rays are 12 centimeters apart and they have a length of 45 centimeters. The rod carries a current I in this direction, as you can see, and it rolls along the rays without slipping. So it is rolling along these rays without slipping. The uniform magnetic field of magnitude this, that is B, is directed perpendicular to the rod. So you can see directed perpendicular to our rod. If and also to the rays. If it starts from rest, meaning the initial velocity is 0, what is the speed of the rod as it leaves the rays? So our objective is to find the speed of the rod. Now, we know the distance that the rod is going to cover when it is leaving the ray. So if we can find the acceleration, the linear acceleration in this direction, then we can use a suitable equation of motion to find the speed of the rod when it leaves the rays, because we know its initial speed is 0 because it started from rest. So we are going to consider it moving in this direction as the equation says. Now, since it is in a magnetic field, then the force taking it in this direction is the magnetic force. Since it never slipped while it was rolling, it means there was friction, indicated as F arrow. So from using second law of motion, we have the net force to be the mass times the acceleration. So the net force is Fb minus F arrow, which is equal to the mass times the acceleration, our first equation. So taking rotatory motion, because it was rolling, so it was moving in a circular path, we have something like this, where it has an angular acceleration of alpha moving in a circular path. So considering the center, this here indicates the radius. Now the force taking it in that direction is still the magnetic force, and we now have the frictional force which acts between this the base of the rod and the rail. Rotatory motion, we talk about the center of mass of the rod, of the circular part, that is of this base, not the rod actually. Taking talk about the center of mass of this circular portion, we have the frictional force times its perpendicular distance, which is ROC from the center, to be equal to the other resistive force, which is the moment of initial times angular acceleration. The moment of initial is just the measure of resistance to changes in the angular velocity. So every rotating body has a moment of initial. Alright, so from there we get the frictional force to be this, equation 2. If we put equation 2 in equation 1, we replace this with F arrow. From there we get the magnetic force to be this. Now our aim is to find the linear acceleration, because finding the linear acceleration we'll be able to get the velocity, the speed. So we need to eliminate the angular acceleration, so we write it in terms of the linear acceleration as this. So the angular acceleration is the linear acceleration on the radius. From there we can fit the equivalence of the angular acceleration with the linear acceleration on the radius. The radius goes down, we have it squared in the denominator. Now the moment of initial of this circular portion about an axis that passes through the center is m arrow squared on 2. So we replace it with its equivalence. We cancel out terms and we get the magnetic force to be this. Now we can look for the LCM. We can now find the acceleration, which is the magnetic force times 2 on 3m. M is the mass. Now we need to find the magnetic force. The magnetic force generally is given by BIL sin theta. L is the length of the rod, I is the current, B is the magnetic field strength. Theta is the angle between the rod, between the magnetic field and the current. Now in this case, we have the current is in this direction parallel to the rod, which is in turn perpendicular to the magnetic field direction. So from there we have the angle to be 90 degrees between the current and the magnetic field. So with that we get sine 90 to be 1. You know the length of the rod as 12 centimeters. Taking it to meters, we have 0.12. The current is 48 amperes and the magnetic field strength is 0.24. With that we get the magnetic force to be 1.382 newtons, 1.3824 newtons. Now we can get the acceleration by simply fitting the respective values using your calculator. You get this. Now we are finding the final speed that the rod is going to lift the rails with. So we can use the suitable equation of motion v squared equal to u squared plus 2as. U is 0, our a is the linear acceleration that we have calculated, and our s is the distance that he has traveled, which is the length of the rail. So with that we get our v, which is the square root of this, and we have 1.07 meters per second.